Okay, these two are difficult. As I try to decide the content limit, I try to look at what questions are asked, both from my final exam as well as the AP exam. These are definitely questions that they're challenging, but you're going to have to know how to do. Yeah, so because we've crossed them off, I wanted you to have more space to do, so you might want to write this down on scratch sheet of paper. But what I'd like to do is I'd like to determine intervals of increasing, decreasing, concave up, concave down. I'd also like to identify the local max, the local min, and also points of inflection. We have 2 parts to our lesson today. We got to make sure we keep pace because otherwise we're going to fall behind, and trust me, it'll get worse as time goes on. So, who remembers what we do to find intervals of increasing and decreasing, local max, local min? First derivative test, very good. When I find the first derivative, what rule do I use? The quotient rule. Derivative of the top is 9. So times the bottom minus 9x times 2x. All over x squared plus 1 quantity squared. So f prime of x is equal to the top. What is my x squared term? Negative 9x squared, everybody agree? Negative 9x squared. Then just plus 9 over x squared plus 1 quantity squared. So the reason why we're doing an example like this is a rational function type problem. And this is going to give you some insight in how we handle this. First of all, tell me something interesting about the bottom. Can't equal 0. Why not? You'd end up with the square root of a negative 1. Okay. Would you guys agree that the bottom is always positive? It's always positive. And what we do is when we take the derivative, we look for critical points. Critical points are where the derivative is undefined or where it's equal to 0. So the bottom is never equal to 0, is it? So all I need to do is focus on the top. Okay? So I can kind of ignore the bottom. The bottom is always positive, always positive. So I'll focus on the top. If I factor out a 9, I'll factor out negative 9. I get x squared minus 1. So that looks like it crosses the x-axis through what points? 1 and negative 1. Is that a parabola that goes right side up or upside down? Upside down because it's a negative 9x squared. So that's the graph of f prime. What we want to do is we want to determine intervals of increasing. Increasing happens wherever the first derivative is positive, which would be from where to where? Good. Whoa, sorry. Don't use brackets. Negative 1 to 1. Because at negative 1, the derivative is 0. And when the derivative is 0, it's neither increasing nor decreasing. Decreasing from negative infinity to negative 1, union with 1 infinity. The local max occurs when the first derivative changes from picture it. Picture a local max. The derivative is changing from positive to negative. Where does it change from positive to negative? At 1. If you plugged in 1, you could get the y value. You plug it into the original. When you plug it 1 into the original, what do you get? 9 over 2. Local minimum occurs when it changes from negative to positive. Where does it change from negative to positive? at -1. If you plug in -1, what are you going to get? -9x. Great, we got everything we needed to from the first derivative test. Now let's do the second derivative test. That means we need to take the derivative of that. Anybody else worried about that a little bit? Yeah, we should be. That's tough. Yes. Yeah. F of x. All right. F double prime. Get ready for it. Derivative of the top. -18x times the bottom, x squared plus 1 squared. Minus the top, -9x squared plus 9 times what? The derivative of the bottom, which requires the use of the chain rule. U squared and x squared plus 1, so I have 2u and I have 2x. So I get 4x times x squared plus 1. All over what? X squared plus 1 to the 4th. What can I get to cancel? I can factor out an x squared plus 1 and get that to cancel. Very good. So that will cancel and drop that to 3, and this will be reduced to 1. So it looks like in the denominator, I have x squared plus 1 quantity cubed. But what about, yes? No, you factor out 1, so it's kind of like this. If I have x squared y plus xy over x cubed, I didn't show the factoring out, but if you factored out an x, you'd be left with xy plus y over x cubed, and you would then cancel that and reduce that to 2. So that's what we did there. I just didn't, to save time and not writing it all out, I didn't do that part. Okay, so what do I have left in the numerator? That's a lot. -18x cubed minus 18x plus 9x squared. I got to multiply it by the 4x, right? Yep. 36x squared x cubed plus minus, wow. Oh, thank you. Minus 36x. Okay, so what do I have for my x cubed term? (18x cubed) minus 54x over x squared plus 1 cubed. Tell me something about the bottom. The bottom is always positive. Everybody agreed? Cool. So I just need to look at the top. What could you factor out of the top? at the 18x, and if you did, you get x squared minus 3. We're going to do something tricky here. Hopefully you don't get upset. Is that just x minus the root of 3 times x plus the root of 3? So f double prime then is a graph that crosses the negative root of 3, the positive root of 3, and 0. And it's a cubic. So, how do I determine when it's concave up? Where is f double prime positive? From negative root of 3 to 0. Union 2. When is it concave down? Where f double prime is negative. From negative infinity to negative root of 3, union with 0 to root of 3. Inflection happens where f double prime changes sign. At what times does f double prime change sign? Negative root of 3, 0, root of 3. How do I get the y values? Plug them back into the original, right? So I would get negative 9 roots of 3. What's the negative root of 3 squared? 3 plus 1 is 4, so negative 9 roots of 3 over 4. What do you get if you plug in 0? 0. And if we plug in the root of 3, we get that 9 roots of 3 over 4. Okay, flip back to your notes. You actually got through the more challenging one. Now we move on to the cube root of x times x minus 8. Okay, cube root of x times x minus 8. Increasing, decreasing, concave up, concave down, max, local min, and inflection. So I told you to take out a scratch sheet of paper. This is the other problem I encourage you to put on there. Otherwise, you could maybe fit this in your notes, possibly. So I want you to understand that you don't really know what this function looks like. Would we all agree? See, on Friday, we looked at cubics, quartics, but what does this look like? And wouldn't it be cool if we could discover that by obtaining this type of information? So again, put yourself back in the shoes of Isaac Newton and others. They would have to go through these processes if they want to be able to figure out what the graph looks like. And it's a really cool process. First of all, I am going to make a note here that this does have an x-intercept at 0 and 8. Would everybody agree that it's going to cross the x-axis at 0 and 8? Those are zeros that we can identify right away just by looking at it. So, you got to be careful not to isolate math to like, oh, are we still doing x-intercepts? We're always doing all math. It's always available, ready to be used. So in order to figure out these pieces, we need to be able to take the derivative. So you have two options. You can either distribute the cube root of x through and then take the derivative, or you could use the product rule. And the product rule is not that bad, and I'll show you why. What's the derivative of x minus 8? 1. So therefore, I'm going to use the product rule. Product rule starts out, what's the derivative of x to the 1/3? 1 over 3x to the 2/3 times x minus 8. That would be in the numerator. Plus, I'm going to raise x to the 1/3 times 1. That's not bad. Let's take a glance at this. I like to find common denominators. What is going to be the common denominator between these two? So I'll multiply the top here by 3x to the 2/3. And look what I get in the numerator. In the numerator, I have x minus 8 plus what? What's x to the 1/3 times x to the 2/3? It's just x to the 1, which comes out to be that 3x. Over what's in the denominator? 3x to the 2/3. So in the numerator, we get 4x minus 8 over 3x to the 2/3. Please ask. Okay, is the denominator ever equal to 0? Yeah, it is. Where? At 0. So we need to check 0. Where else is the numerator ever equal to 0? At what? At 2. So there's nothing nice about this. We don't know what the graph looks like because both the numerator and denominator, we're going to have to test. So we just plug in some points to test. What's the number to the left of 0 you could test? -1. So if I type in -1, I get 4 times -1 minus 8. That's a negative. Okay, that's a negative. Divided by, now I'm going to put -1 in here. -1 squared, cubed root, times 3. So I get a positive in the denominator. So is that answer going to be positive or negative? So it's negative here. Now we'll try 1. If you plug in 1, what do you get here? You get a negative, right? And if you plug in 1 to the denominator, you get a positive. So therefore it's negative. Now what would you like to plug in? And in the numerator, you get a positive. Divided by a positive is positive. Very good. And so you get a positive. So what does this help me identify here? Yeah, it looks like in this situation that I have a, where it changes from negative to positive, that's going to be a local min. So the local min happens at 2. And if I plug in 2, I get -6 times the cubed root of 2. Do I have a local max? No. Where is it increasing? Because it never changes from positive to negative. When is it increasing? 2 to infinity. When is it decreasing? Negative infinity is 0, and then union 0 to 2. Kind of wonder what the heck is happening at 0. It's rather interesting. We've got to come up with a second derivative now, don't we? I think I have a way to make the second derivative easier. Would you like to make the second derivative easier? Everybody game for that? Okay, so again, I'm trying to show you some tricks of the trade here. If I see this, and so this is a problem, so I pulled this problem, I can't remember what year it was from, but I pulled it straight from an AP exam problem. If I got to find that derivative, I write it as 2 fractions first. So that's f prime, correct? So I write it as 4x over 3x to the 2/3 minus 8 over 3x to the 2/3. Would you agree that this is 4 thirds x to the 1/3? And would you agree that this is 8 over 3 x to the negative 2/3? So let's find the second derivative then. What's the derivative of that? Close. I drop the 3 in front. I get 4 over 9. X to the negative 2/3. Dump the negative 2/3 in front, and we get plus 16 over 9 x to the negative 5/3. Good. We're getting closer here. So that's another way to find a derivative. So I have the derivative using my negative exponents, rational exponents. Again, I'm just trying to give you some tricks of the trade. So this would be 4 over 9x to the 2/3 plus 16 over 9x to the 5/3. I'm going to show you how to take care of this because it's really not too bad. We've got to check something here. And when I want to solve for where this is equal to 0, what I like to do is I like to find the common denominator. What is going to be the common denominator here? 9x to the 5/3. So what would I have to multiply top and bottom by to get 9x to the 5/3? X to the 3/3, right? Which is x to the 1. Multiply top and bottom by x. That's all we have to do. So on the top, I get 4x plus 16. And in the bottom, welcome. In the bottom, I have 9x to the 5/3. We've got our second derivative. Where's the top equal to 0? No. Negative 4. It's okay, we're trying. Where's the bottom equal to 0? At 0. Looks like we have to do some testing here. What number would you like to test? Negative 5. If you put a negative 5 in the top, are you going to get a negative or a positive? Negative. And then if we take a negative to the 5, if you take a negative to the 5/3 powers, that can be positive or negative. It can be negative, right? So we get negative or negative, which is a positive. Okay, what number between negative 4 and 0 do you want to plug in? Negative 2. So I try. 1 is not between negative 4 and 0. 4 times negative 2 plus 16, positive or negative? Positive. If I plug in a negative, the bottom is going to be negative, so I get. Rachel, what would you like to plug in? 1. And we get positive over positive, which is a positive. What does that tell me? What does it tell me? What does that tell me? Concave up where? Good job. Concave down? Do I have inflection? Inflection is where it changes concavity. Inflection, negative 4 and 0. Could we find out the y values? Plug it in the original. If I plug in 0, what do you get? You get 0. And inflection, cube root of negative 4 times negative 12. That's going to be positive, right? Well, cube root of negative 4 is negative, and negative 12 is negative, so it's going to be positive. So 12 cubed roots of 4 is what we get. All right. So let's see if we get what we thought we were going to get, and we'll end for the day on that. Math, I've got the cubed root of x times parentheses x minus 8. Zoom 6. Let's see the picture. Look at that crazy shape. Now look at how it starts. Look at how it starts. Right here, concave up or concave down? Yeah, it looks like it's really, really slight. But in this situation, it starts off until we get to -4, it's concave up. So it's concave up here, and then turns concave down here, and then turns concave up here. That's what's happening. Look at what else we found out. Where did we say across the x-axis? Across the x-axis at 0 and 8. Look at its, is it increasing or decreasing? Decreasing all the way till 0, right? Notice what happens at 0. What kind of tangent do we have at 0? That's why it says that it's neither increasing or decreasing at 0. You have a vertical tangent. Do we have a local max at all? No local max, do we? Do you have a local min? Yeah, there it is. Local min happens right at an x value of 2. So they could have graphed that function, though it'd be pretty difficult, but they could come up with that sketch. So excellent, excellent, excellent work.